So for the benefit of the recording, I'm just going to repeat what this session is going to be about. So yeah, so we're going to go over some built-in analysis tools in analysis that are sort of that enable you to analyze your systems. So there are some methods that are acting upon positions, and this means that positions are a property of a particular time step. And so you are going to have to build, you're going to have to basically iterate over the trajectory and run the analysis and get the results for each frame. There's another class of analysis methods, which instead they act on atom groups. And that means that instead these functions, they take care of iterating over the whole trajectory on their own. And then the final thing we're going to go over is how to create your own analysis tools with MDAnalysis objects. All right, so the first example that we have is kind of taken from the previous tutorial. We are going to use the same PEG example. Oops, need to run this first. All the imports. And we're going to retrieve again this polyethylene glycol trajectory, which you have used before, which features a polyethylene glycol chain in water. So what we want to do is we want to iterate over the trajectory, calculate the, for each frame, calculate the radius, return the radius of gyration, and plot the result. And here you go. So we have, so we create an empty list to store the results. Then we iterate over the trajectory. And then we plot the corresponding results. So here we are appending radius of gyration to this. Right. So simple as that. And so now we can do the same thing for other properties. So we have just done the center of the calculation over the center of geometry, for instance. We can do the same thing with the center of mass. So we can use some of these kind of built-in methods that act on positions. So for instance, if we wanted to calculate, I don't know, the center of mass for these, for the same atom group, we could do that. And again, like before, we have center of mass components, X, Y, and Z as a function of time. Which, yeah. So next we're going to move on to look at some of the other more kind of complicated built-in analysis functions in the library. And we're going to start from the radial distribution function, the otherwise known as RDF. So this the RDF is quite useful across sort of if you do any molecular dynamic simulations of fluids, of any kinds of systems, solids, liquids, anything really, you're probably going to at some point need to calculate a radial distribution function. So essentially, if I am the red dot at the center, what I'm trying to figure out is what is the probability of finding another atom at a certain distance from the red dot. And yeah, so the radial distribution function describes the probability of sort of finding different atoms at increasing distance. And so that means that you have to do a lot of pairwise distance calculations for each atom in your system or subsets of atoms in your system. So this is where the underlying implementations of distance calculations come very handy. That this is all stuff that's going on under the hood in the RDF function. So we're not going to look into in detail as to how these distances are calculated, but we have sort of looked into it already because we have talked about capped distance and distance arrays. So you can imagine that basically that's going to be the basis of the implementation of this function as well. So we're just interested in the results now. So we're gonna go ahead and calculate the RDF between the oxygens of water and the oxygens of our polymer, of our PEG. So we define two atom groups. So the first one is type OW, which is water oxygens. And then the other one is our PEG oxygens. And then to calculate the RDF, this is as simple as calling RDF.inter-RDF. And we need to provide, at the very minimum, two arguments. So the first one is one atom group, and the second one is also the other atom group. So in this case, we have oxygen, water, then we have oxygen of polymer, and then we can also specify the range, which is which range of distances we want to calculate the RDF for. So in this case, we are going from 0 to 10 angstroms. Remember, always MDAnalysis units in angstroms. And so when we run this method, nothing actually happens. So in order to actually calculate the RDF over the whole trajectory or parts of it, we actually have to call this oxygen RDF.run function. So this also runs pretty quickly and returns a kind of this results object that has the bins, which are kind of like the bins where we calculated the RDF for, so that all the different distances between 0 and 10 angstroms, and the actual value of the radial distribution function, which is returned as this RDF. And this can also be returned, can be also called like this. So RDF.results.RDF. It's like a couple different ways of getting this out. So we can now finally plot this. And this is our oxygen RDF, where we've also added a dotted line around 1, which is kind of the value that we'd expect that the RDF should converge to at larger distances. So the RDF is a function that has a lot of meaning at kind of medium close distances. So in this case, for instance, we expect the probability to kind of like taper and converge towards 1 as the farthest we go in kind of this in radius. So mathematically, we know that the RTF should always kind of converge or tend towards 1, right? So in this case, we see that there's some close contacts around 3 angstrom, which is you know, what we would expect to find, and then we have kind of this second peak around 5, and then we have kind of a bump, and then yeah, not much else. And of course, we don't expect to have anything between 0 and 2 because that would be a little bit too close for comfort. So this is all nice and well. And it is a little bit noisy because we only have something like less than 100 frames in total. So obviously, the more frames you have, the more kind of smooth the profile that you get. So if we go back, for instance, and try to run this method, but then we can, for instance, select only a few frames. So in this case, we can say, so we have this start, stop. I think this was 90, I don't know, we can say 90 just to make sure. I think we definitely have at least 90 frames. Sorry? 98. 98, okay. And then we can say step equal 10, for instance. So this would be equivalent to say start from the first frame up until the 90th frame, and then but just calculate the RDF every 10 frames. So again, we got the same. So the bins, they haven't changed because we have kept the same interval between 0 and 10 angstroms. And now we get something that looks even noisier because we used even less frames. But for instance, this can be interesting for you to kind of as a quick check. You know, if you have a very, very big trajectory, you can load the you can load this as a universe in MDAnalysis, but then if you don't want to wait for a long time for your whatever calculation, be it RDF or something more complex to run, you can always try and test your analysis on a much smaller subset of frames. And then if you see something that doesn't look right, speak to someone, sorry, BTP. But yes, so if you see that, you know, your results make sense, then you can kind of go on and do the analysis for longer for more frames. So that's always useful to know. Right, so the other built-in function that yes, that's a very good point. So we can change the bin in. Let me just, so I actually don't remember exactly, but I'm gonna call out the doc string. Oops.
Can you repeat the question, please, Micaela?
Sorry, yes. Yeah. So the question was, how do we change the binning? So can we kind of sample more often? And I'm gonna just check our doc string. So there are several arguments. So here, the third argument is n bins. So I can insert that here. N bins equal. So this is the default is 75. So I don't know, I can put 200 maybe, see what comes out. And so, and I'm going to run this again. Now we have a lot more bins. Well, a few more. And let's see how our plot changes. Yeah. So less noisy than before, but still pretty noisy because we still don't have a whole lot of frames, right? So you have a lot of different arguments. Another argument that is I personally find very interesting. Let me see if I can call that out again. I think I minimized that out of the way, which is a pity. there it is. So let's go and look at the doc string again. So there's a very useful argument here called exclusion block, which is very helpful if you're running an RDF. For instance, if you wanted to look at the RDF of water, right? Or if you have, for instance, so if you wanted to run an RDF of different polymer chains, right? If you have different PEG oligomers in the simulation, but you want to have an RDF between the different chains, but not the atoms in the same chain. So you can have you can define an exclusion block to basically prevent yourself from calculating the kind of the contacts that you don't want to see in the RDF. So let me see if I can explain myself better. So if you have, if you're only interested in intermolecular contacts and you want to exclude the intramolecular contacts, then you can use the exclusion block to say, for instance, if you know that, let's say I have 10 oxygens in each PEG chain. So I want a 10 by 10 block to exclude because I only want my 10 oxygens of each PEG chain to interact with the oxygen of different chains. And so if I calculate the RDF, including the kind of the first 10 by 10 block, if that makes sense, I would be calculating the RDF between oxygens that belong to the same polymer, and I don't want that, right?
But I need a file, a structure file which has the the correct numbering, like the molecules in.
So the question was, do I need to have this information in a file? Well, you need to know your system, right? So you can, for instance, even just inquire, like print out if you know the order in which you have defined your polymer, you know how many oxygen, like in this case, we are just looking at
residues or molecules.
Yes. So you would just need to know your system.
Okay.
But just like any other analysis. So this was a very specific case in which I'm assuming that I have a subset of atoms in each polymer, of which I want to look at the interactions between those atoms and the same kind of atoms in different chains, right? And so obviously for a different system, it could be like a completely different scenario, but I don't know, this kind of came to mind first. But yeah. So to summarize, exclusion block is useful if you want to exclude certain subsets of atoms from this RDF pairwise distance calculation. Yes. So, and it's also explained in the doc string. So I would say first the first port of call would be to just check the doc string, check the documentation, because usually you'll be able to find an example for all the arguments. So, right. Okay. So moving on to the next function, we have the persistent length, which is also something that might be interesting for people working on looking at macromolecules, polymers. I'm not sure about proteins, because proteins just tend to fold in very specific ways. So I'm not sure that you ever want to calculate the persistence length of protein, but somebody might correct me. So the persistent length is basically a measure of how stiff our polymer chain is. And so if you have, so imagine this, the difference between uncooked spaghetti persistence length is very long, right? Because the correlation between the vectors in defining the polymer direction is very high. So the object is completely rigid. Or cooked spaghetti, where it's kind of much more flexible, and so you have very short segments that are kind of approximately linear, but the whole object is extremely not linear. So we have a function in this MDAnalysis.analysis.polymer library that is called persistence length. And so in this case, we want to calculate the persistence length of this small ethylene glycol chain and using the atoms in the backbone. We are going to exclude, for instance, the hydrogens, because ideally, when you want to calculate the persistence length, you want to have something that is, you want to use a number of atoms, and the atoms that are sort of as basically in the backbone as much as possible. So you don't need to have some kind of spurious effects by considering extra atoms. So in this case, we are going to use all the carbons in the backbone. That means we have 40 atoms in total. And something to to remind ourselves of is that when you do an atom selection, your atom selection will be kind of sorted in ascending order. So in this case, for instance, we can check that is true by looking at the backbone atoms that we have just selected. And so we have C, C1, C2, C3, C4, and so on. So that means that we are starting from the first carbon and going all the way to the last one. Why is this important? Well, because to calculate the persistent length, we need to have all of our vectors in a very in order, because otherwise this measurement doesn't make much sense at all. So in order to use this method, we can call persistence length, we can provide the atom group, and then we can call run again. So all these methods are basically sort of the way to remind yourselves whether a method can automatically iterate through the trajectory or not is if the use case involves calling the method .run, that it means that basically what that .run is doing the calculation over the whole trajectory. So in this case, we can again look at the results, looking at pl.results. And here we have a bunch of stuff. So we have the value of the bond autocorrelation. Then we have the X, which is basically the one of the our distance. And then we have the fit of the function. So this already performs the fit of our autocorrelation function. And so we can just plot all of this here. So we can plot the X as a function of the autocorrelation. And then we can plot the our X as a function of the fit. And so we have our dots, which corresponds to the values of the autocorrelation function calculated as an average over the whole trajectory for our chain. And then we have the fitted function, the corresponding fitted function. And then we can also, so from the fit, we can also get the value of the persistence length, which we obtain, which is, in this case, it's 3.7, 3.8. So when you run this persistence length function, it is automatically calculating the bond autocorrelation and also performing the fit at the same time. So the next function is a big old classic, root mean square deviation. I'm sure that probably most of you have or will have run one of these at some point. And so in this case, root mean square deviation is essentially a measure of how each frame is similar, or how the coordinates of your object, your protein, your polymer, your system of interest are similar to each other, basically, to themselves, to some kind of a reference point as a function of time. So in this case, we're going to use this ADK trajectory as our test case. And here we have a very long explanation about the RMSD that you can revise at your own leisure. So we're going to do two things. So the first thing is we are going to do a very simple RMSD calculation between the kind of a reference set of coordinates and another set of coordinates. So in this case, for instance, we have defined our universe where we are loading the trajectory, where our ADK is in the closed conformation. And then we have a coordinate file where our ADK is in the open conformation. So we expect these two to be somewhat different. And so we can calculate the root mean square deviation between our coordinates. So the reference coordinate, which are were they open or closed? Open conformation, and this is closed conformation. And so this gives us an RMSD of 6.8. But actually, what we mostly want to do, we don't really want to often calculate the RMSD between two individual sets of coordinates. What we want to do is we want to get the RMSD as a function of time. So looking at things like diffusion coefficients and so on. So that's kind of the main use case for us. So we can do that by calling the RMSD capital RMSD. So in this case, we want to define the three subdomains of this ADK protein using the core domain, the one that doesn't really move much. And then you have the lead and this NMP. And then we can calculate the RMSD where we provide twice the same universe. And we want to basically calculate the RMSD between of each individual subdomain of the protein. So we run this function. We use the first frame as reference, and then we get the results. And we can, so for ease of plotting, we can put all these results in a pandas data frame where we have the frame of reference, the time in nanoseconds, and then we have basically 4 columns for each. So we have the backbone, so of the whole protein. Then we have the core domain and the lead and the NMP. So this is kind of a way of processing this data a bit more nicely. And then we can just plot it using the plot method from the data frame. And so here we have the root mean square deviation for so the blue line would be the kind of what we could consider as the kind of average of the whole backbone. Then we have the core of the protein that doesn't really move as much. It has the lowest RMSD of all. And then we have the other two domains that are kind of involved in this opening that are the ones that kind of have the highest RMSD. So this is kind of a way to, you have a little bit more of a, larger system, different subdomains, and an example of how to integrate NumPy, pandas, MDAnalysis methods, and visualization with matplotlib. Right, so far we have seen different examples of analysis tools that are already implemented in MDAnalysis. So some of them are, again, acting on a particular set of positions and the positions at a given time frame. And so that means that usually in order to get the whole trajectory analyzed, you have to yourself iterate over the whole trajectory, calculate the property, save it in some kind of a list, an array or something else, and then retrieve the results and plot them. Or you have other more kind of complicated or kind of longer, more complex analysis tools that are mostly kind of very universally used. So like root mean square deviation, RDF, so analysis that regardless of what kind of science you're doing, you're probably going to use them at some point, right? And so these are already implemented in MDAnalysis, and you don't have to, so each of them has a very similar structure where you have to provide your atom groups as an input. You have to provide some kind of potentially sub-selections or options. So for instance, atoms to exclude in the case of RDF, or other options in terms of the input. And then you usually have to sort of run them using this run function. And then at that point, you can specify how many frames you want to run the analysis for. So you want to do the whole trajectory, you want to do start from, at some point, you want to have a different step. So yeah, so basically the nice thing is that they all kind of work in the same way. Some individual options will be different, but kind of in the end, you all, so for all of them, you always have this run method, and then the results are always retrieved in the same way. So that makes things nice and mostly uniform. Right. So this is quite convenient because at this point with MDAnalysis, we have developed this standard way of, thinking about analysis tools. And that helps us because we can use the same structure, the same frame that we have seen, for instance, in the RMSD function or in the RDF function, and we can just apply the same template to write a different kind of analysis. So for instance, if you have, a specific property that you want to analyze of your system, you can go and take this template and apply it to your system. And so this is what we're gonna see in the final part of this tutorial. So usually the classic way that you approach, your kind of devising a new analysis, you can do it in different ways. So you can first maybe test your analysis on a single frame, then package that analysis into a function and run that function for a series of trajectories or one or more trajectories. But if you're using this new analysis that you have developed, if you're using this pretty regularly, then it's going to become maybe something that you want to formalize a bit better, maybe turn into a class and have it you know, as something that you can import in your analysis scripts. And so this is where the kind of analysis class from MDAnalysis can come handy. Right. So, and of course, if you get to the point where you have a specific analysis that you think might be useful to other people in the community, and you have used MDAnalysis tools to develop it, we always welcome contributions to the code. So you can contribute to the code base of MDAnalysis, or you can make kind of your own package that features that has a MDAnalysis as a dependency, and we can kind of help you with that as well. Yeah, so for instance, here we have an example with the radius of gyration, which we have encountered before. And we can just basically define this as its own function, which is already written down here. So this is what happens when you call the function radius of gyration. So we're gonna load again this example universe. And then now that we have defined our radius of gyration as a function, we can use this MDAnalysis analysis from function to turn our function into something that works exactly in the same way as the RMSD function or the RDF examples that we've seen before. So we can define this ROG as analysis from function, and we gave the arguments are the functions we defined. Then the trajectory that we have to iterate over. And then any arguments that are important. In this case, we have the atom group that we are calculating this, the radius of gyration for. And then, of course, we need the protein, the masses of the atoms, because, of course, this is goes into the calculation as well. Right? And then the total mass as well. So any argument that is needed by your function goes here. Oops. Yes. Then the results are going to be returned in the same way as we have seen for the other functions. So you have this like dictionary that has the various frames and the results as a time series. So, oops. Yes. So we had 98 frames. So we have time series that is 98 by 4. And so now we can plot the radius of gyration as a function of time that we have just calculated with our nice little analysis function. And so this obviously is just a simple example, but you can think of your own, you know, whatever property you may want to or need to calculate, and you can kind of apply the same principle to your use case. And then just to remind ourselves of you can run this analysis over the whole trajectory, just like we did, or you can just select different sort of start-stop points and steps. So in this case, we are playing. So the input here is the same as before, but we are just running this analysis starting from the 10th step and every 7th step. And so, yeah, that looks a little bit different. but maybe for, you know, whatever you're doing, that's plenty of information. Right. So this analysis from function was sort of a quick and dirty way of applying the same custom template to a very simple function that we wrote. But there's also something a little bit more elaborate you can do. So you can transform your simple function into an actual class. So in this case, you can apply this analysis class to the function instead of using this analysis from function that we used before. And so in this case, we define this class called radius of gyration with capital letters. And we just called this using analysis class and then the original name of our function. And then everything else is pretty much the same, except that now we run this radius of gyration like as if we were running exactly in the same way that we were doing the, for instance, the RMST calculation or the RDF calculation. So now the syntax will be exactly the same. So the input that we need now is simply whatever was the kind of input variables of the arguments of our original function, right? And then the results you can retrieve them in the same way. And so we have the same result as before. And this is kind of a short demonstration of how you can start to think about, you know, exploring data, formalizing your analysis scripts, and then kind of using MDAnalysis built in the structure that we have to kind of go from this data exploration phase where you are visualizing the system. You can use NGLview, you can use obviously other tools, but if you find that this kind of notebook-based analysis and notebook-based data exploration works for you, in these notebooks, we have basically demonstrated how your analysis workflow could work. Right. So yeah, so the final appeal that I want to reiterate here is, yeah, if you come up with a fancy new analysis method that works for your system, odds are that maybe some other people in the community might want to also do the same analysis. And so if you find yourself in that position, consider contributing to MDAnalysis, consider maybe writing, letting us know how you're using the package on Discord, on our GitHub discussion page. And yeah, so great. Cool. So I'm gonna stop sharing and head over to grab a coffee. And yeah, I'll probably leave the laptop here anyway. So I'm just gonna mute myself. So see you in a bit.
See you after the break.
Right, so yes, this session is going to be a bit of I don't know what's going to happen. So, Richard, did you want to, I don't know, did you want to go over examples?
Yeah, I've got
or
the session for Notebook ready, and I've also put a couple of requests we had so far, and I've tried to do them. But if people have other questions that they've encountered today, then I don't mind trying to solve their questions live. It's a fun challenge at the end of the day.
All right, so how about you fire up the notebook and get started, and then I will gather any and every question that I get in the room, and then I'll relay that to you.
Yeah, like I'm game for any challenge there is. So.
Ooh, okay.
All right, let's see if we can beat the champ. That's how we're doing this. It's King of the Ring. If you can win, then you get to present. So
Alright.
I'm going to skip past the ones we already had. Someone asked me earlier about adding an arbitrary property to a universe. Like, could you define your own property and then select?
Yeah.
Right. I didn't know this until I started looking, but turns out you can. So sorry, this is, maybe I should duplicate this here. So if you make a new universe, so here I'm just making an ADK universe, it doesn't matter. I'm going to import something from inside the MDAnalysis library. You're probably not meant to know this exists. This is sort of digging into the internals of MDAnalysis. I'm digging into sort of .core.topology attributes here. But if you import this thing, you can define an attribute called bounciness. So I'm going to define if an atom is bouncy or not. Just to prove to you that it's not a real attribute. And there's this method, universe.add topology attribute, and you can add bounciness. So I've defined bounciness as Boolean. You see the true, false if you're bounciness. It could have been a float value. You could maybe quantify bounciness. I thought that would be too advanced for today. And you have to define a few other bits, but you can find code examples in the library of how this works if you are sort of developer-minded. And so I've added it. I've called it zeros-like, so it's sort of starts off as default 0, which is false or Boolean. So basically none of the atoms are bouncy. And if I try and select by bouncy, I get, an empty atom group. But then if I say the first 10 atoms are bouncy, and then select atoms bouncy, all of a sudden I get 10 atoms returned. If I did something crazy, like I said every other, I haven't run these cells, that's what's happened there. If I say every other atom is bouncy, then I can say bouncy and back. I get, all the atoms on the backbone that happen to be called bouncy. So this is highlighting the fact that MDAnalysis is actually quite flexible, and a lot of the attributes are defined dynamically and sort of made up on the spot. And this is how we handle so many different file formats, because different file formats are going to define a lot of really different attributes. So for example, when you're loading things from RDKit, they start to define things like aromaticity of atoms, which is obviously a bit of a strange concept to regular molecular mechanics. And so this is how we've managed to handle all the file formats. So it's actually quite flexible if you dig into it. The slightly easier question I had was, can you select hydrophobic, hydrophilic groups? I think one way of doing this would just be to try and look up which residues you consider either hydrophobic or hydrophilic, and just sort of, you can put them in here. So I've done res name, 3 res names here. This would select this or this or this, so any one of those 3 res names. And similarly for your hydrophobic groups, you could list them out and just select based on them. This is sort of how the backbone and protein selections, which are built into MDAnalysis, also work as well. So there's that. If you wanted a more nuanced description of hydrophobicity or hydrophilicity, where you're actually looking at dipole moments and things like that, then that's probably a bit too advanced for what you can do with select atoms. You're probably going to have to do a bit of manual work to pull out those selections. So that was 2 fun questions that we had in. I'm happy to take any more. I've also got some sort of pre-made things. The other thing I'm remembering is, Micaela, did you want me to present about the NDA kits thing as well?
Yeah, we can maybe do it at the
end, maybe.
Or,
yeah, okay, sorry, just before I forget. So this is stuff that I've added to the tutorial 4 notebook. At the end, I'll probably upload this at the end of the day just so you can find it, but I'm going to rewind to the start of this tutorial 4 notebook, which I think you all have in your workshop materials. So this is like in session 4, Advanced Universe Creation and Attributes. So I'm going to scroll down from here. So this is something we've sort of alluded to before, which is a bit advanced and a bit complicated. We've been saying a lot that MDAnalysis only loads a single trajectory frame into memory at one time, and that's to make it, work on a workstation that has RAM that's smaller than your trajectory size, if you think about it that way. You can, however, not do this. So there's this method transfer to memory, which, kind of gives itself away what it does. So if we load a regular universe here of this ABK system here, and we're going to use the Jupyter Notebook magic descent sign, time it. This is kind of handy for benchmarking things because it will tell you how long it takes to run this line here, where we're basically creating a list of the frame index for every frame in the trajectory. Where here basically we're timing how fast we can go through a trajectory, basically, because accessing the frame index takes 0 time. So what we're really benchmarking is this for loop over the trajectory. And we can see that this takes 170 milliseconds. If I basically pass in memory equals true when I load a universe, it loads the universe in a bit of a different way, in that it will load all of the coordinate data into the universe on creation, which is obviously going to take up a larger amount of memory on your system. And if you have a very large trajectory, it might make everything burn in a horrible way. But we can see that the time to iterate through the trajectory is now dropped to about 5 milliseconds, which is, compared to 170, that's a lot quicker. And so if you are finding analysis is a bit slow and you're having to iterate through the trajectory frequently, and you're doing it on a quite kind of a beefy workstation, maybe you're doing it on your HPC, this is the way to get a bit of performance. A strange thing about analyzing molecular simulation data is that often the rate limiting step, the thing that's making all your analysis slow, isn't actually any of the number crunching you're doing or any of the code you've written, but instead it's just taking the data off the disk and putting it into memory, right? And so sometimes it doesn't matter how nice code you write, it's just the disk is being slow. And this is one way around that. Okay. All right, second fun example. We have this guess bonds method, which is super cool because often the files that we're loading don't have bonding information defined in them. So for example, a PDB file sometimes doesn't have bonding information included in it for various reasons. And that's a very common file format. Similarly, if you have something like an XYZ file, there's obviously no bonding information in there. So you often need to guess the bonds. It's quite simple to do mathematically in this equation here, where if the distance between I and j is less than the 2 covalent radii of the atoms times by some sort of what was called a fudge factor, but basically a threshold. If the atoms are too close to each other, you assume that they are probably bonded, basically. So, it's going to try and download a gigabyte. I don't know why it's doing that. Okay. Oh, doesn't like that I did that. Oh yeah, atom group fragments not available. This requires bonds, right? But if I run this with guess bonds as true, it would try and guess the bonds, but it needs to know the van der Waals radius of each atom. So you can also pass that as a dictionary here. So I think it got confused here, or would get confused here by the chlorine and the sodium diameters or radii. And so if you pass these as in a dictionary, this would fix that. And if I just copy this, maybe I can show you what error message you would normally get. This should work unless I've killed the notebook when I killed this cell up here. Not sure if I've killed the notebook here, but anyway, this is something which makes guess bonds even cooler, is that you can provide the radii yourself, which means that you could even guess bonds if you had, for example, a coarse grain system. So if you're working with a Martini system, you still know the radii of your particles and you can still guess the bonds on them. That's worked without the van der Waals radii. I'm not sure what happened there. Anyway, this is a cool feature of guess bonds, which I think a lot of people would benefit from. Okay. Here's another, assuming I don't have any requests from in the room, here's another fun feature that not a lot of people know about, that I think more people could benefit from, is the chain reader. Oops. So often when you run molecular dynamics simulations, you have to maybe restart your calculation a few times due to wall time limitations, or maybe sort of you run, you know, a certain amount of simulation time and you realize you haven't quite captured what you want to sample, so you run a longer trajectory. And so what you can often end up with is lots of different trajectory files, which are all the same system, but you had to keep restarting it. So here I've got a list of trajectories, and you can see that they're all different BCD files on my computer. So what you can do is, if you pass this list of trajectory files into the construction of universe here, so here I'm passing a topology file, I can show you what that is. So here, this is just a PSF file, and my trajectories file is, as we can see, it's a quite long list of trajectories, right? I can pass this list of trajectory files in here, and it will magically load all of the trajectory files at once, or it will stitch them all together into a single trajectory, even though it's multiple files. And so it will be opening and closing the files that needs to walk through that list of trajectories. And if we look at the details on this trajectory object, it's saying that it's a chain reader with this file and 199 more. So it's got 20,000 frames. Whereas if I would have just loaded the first file in that list, I can see that this has only got 97 frames, as if I load. I've now got 20,000 frames. So if you have lots of frames, you can stitch them together using MDAnalysis. That's quite common. It means you don't have to reformat the whole file. Cool. This is a fun, interesting thing if you work a lot with biochemistry. Is we've got fetch MMTF, which will fetch a MMTF file from the PDB. So if you know what a molecular, what's this stand for? Macromolecular transmission format. If you know what an MMTF file is, you can just type in your PDB code here and it will load the universe of that MMTF. So if you know what that is, that's very useful to you. If you don't know what that is, you're not missing out on much, I think. Okay. Okay, so another cool thing that people often have to do, which is a bit of a strange use of MDAnalysis, is that you can sometimes create a new universe without having any files to start with. So maybe you're constructing your own system, or maybe you're bringing in the data from lots of different files, and so you don't have a single topology file which is describing your system. And so what we have for this is there's a universe.empty method, which will create a universe without a starting file, is how to think about that. And so you can look at the help for this. The way to get help for anything is you can just type in the function or method with a question mark after it, and a Jupyter notebook will bring up the help. And this then shows you all of the arguments for this function, and it will give you a description of what all these different arguments do. So we can see here that it wants to be given a number of atoms, a number of residues, a number of segments, a number of frames, and sort of will it attach a trajectory to this universe as a Boolean true or false, right? And these arguments here, which have a default value, they're optional because they come with a default value. So here I'm going to make a universe with 21 atoms, 7 residues, and it has a trajectory attached. And we can see that, you know, magically it's made a universe from nothing with you know how I defined it, and it's atoms by positions, and we can see that it has atomic positions for those atoms because I put in trajectories true, but obviously they're all 0 to start with because it didn't know what the positions were. But you can edit that, obviously. So if you're pulling in those positions from somewhere else, this would be a way that you could start to construct a universe in a strange way. And similarly, we can put the atoms into residues if we wanted to start grouping things in. And we can then add topology attributes as well. So we could start to give our atoms mass, and we could give them names, and we could give them atom types and res IDs. So here we're assigning them all a mass of 10, which is a strange atom, but you can do it. So now if we do u.atoms.masses, magically they will have an atom of, they will have a mass of 10. So hopefully you can see that if you're working with a strange file format, maybe you're converting it from a different data source, or maybe you're even doing, you know, some advanced code where you're, who knows what you're doing. But if you're working in a strange way and you want to create a universe, this is one way to get there without having to write files out and go back from a file. And then finally, if you really need to, you can then write that out to a file. And so if I do u.atoms.write, it will write it, and then I can see that I've, you know, written out this crazy file that I created. So I've written out my universe, and I can see that they're all called A, an unknown residue. But you know, it's a start. And
Richard, can I just interject 1 second? Because I think something that I realized that we haven't explicitly covered is you can create an empty universe, you can edit all of these attributes, but you can also edit and add attributes from existing universe, even though, or you can overwrite sort of atom types, atom names, masses, anything that you may have on an existing universe. You can also overwrite any of those. So I don't know if that's something that people have already picked up on, and we have maybe slightly touched upon it, but we haven't explicitly discussed it. So I just wanted to make sure that, yeah, this is not just for an empty universe, but you can do it for any, in any case.
Yeah, something I've previously had to do actually, which is quite strange, is I actually had to merge two topology files together when I loaded a single universe. So I had one file that had some of the data I wanted, and I had a different file that had some of the data I wanted. So I would load two universes, and I would sort of mush them together, like you're saying. I think one file had the bonding information correctly, and one file had the I think atom names or something. So yeah, you often do have to smush together files. Do you want a example of that, or?
Yeah, you can demonstrate that if you want. That would be nice.
Let's try and figure this out then. I'm going to copy this line to cheat. So I'm just going to cheat and see which attributes I have here. So I'm trying to think of a good example here.
Or you could
yes.
just show how to merge two universes, regardless of which attributes they have, right?
Yeah, that's a whole, yeah, so I was just thinking, so if I load this universe here, I could then, if it was missing a certain attribute, and I was trying to find out which attribute it was missing. But if I wanted to add a topology attribute to this, you can do it with this method here. And so if I had that on a different universe, let's just cheat and load the same universe again. I'm going to call that U2. And u2.atoms.names is, I'm going to rename them all to XYZ just for the sake of the example. I could then sort of place it from the other universes attribute.
Wait, we have a question. Yeah, so can you add dummy atoms as well?
Oh, the short answer to that is no. So the one thing that's really hard to do in MDAnalysis is to add dummy atoms. So it's very difficult to change the number of particles in a data structure. But now I've thought about it for a couple of seconds. Challenge accepted. So I'm going to say this is my universe, and then I'm going to use the thing I said before about NDA.universe.empty. I'm going to say n atoms is 10, so I'm going to say I have 10 dummy atoms. And then I'm going to say merge. So there's a MDAnalysis.merge method, which It's a bit like appending two lists together. So let me see, it wants one or more atom groups. Okay. Let's see if this one can explode in my face. So there you go. So I've merged these two universes together. So now that I've gone from having 3,341 atoms to 3,351 atoms, where I have 10 dummy atoms. So I'm going to call this one new. And then if I look at the last 10 atoms here, the universe does not contain name information. So I think what it's done is it doesn't have any names because it reduces down to the common subset of different attributes. So then if I had add names to there, create that again. Now I can see they're all called dummies. So what did we learn today? You can merge two universes together, but it'll only have attributes that both universes have in common. So it's kind of useful, but also a bit tricky to use. So I'll go through that a bit slower. So I made a universe. I made a new universe, which was empty. Because it's empty, it didn't have any atom names. So I added in the atom names. I then used the merge function that would merge these two things together. When it found that the second universe didn't have a lot of attributes, it just dropped them from the first one. So basically deleted a lot of information when I merged the universes together. So I sort of added in names, and I can see that my new universe has dummy atoms at the end. So it's essentially concatenated these universes together. This is often handy when you've maybe saved your solvent separately to your solute and things like that. You can play tricks like that.
Yeah, we have a question in the room.
So for anyone that didn't hear the question is, can I essentially do the opposite of a merge? Can I separate out one universe into two? Things like that. I think there's two answers to that question. One answer is, because you can just use select atoms, you often don't have to separate them out. So that the memory footprint of MDAnalysis is quite small, and so if you want to ignore your solvent, often it's safe to ignore your solvent. But to entertain the question a bit better,
Can I actually disagree with that? I think maybe if you have a very if you have a ton of solvent molecules that you don't want to download with your trajectory because you're not going to analyze them from the HPC, maybe you want to have as kind of a smaller version of a trajectory that only has the thing that you are interested in. And I think there's a lot of tools that allow you to do that. Like I think Gromax, you can save just some of your system and it creates a new file. So you can definitely do that. And I can think of cases where you would want to.
Okay, I will entertain the idea. So I've loaded in a Gromax simulation here. So I've loaded in a TPR and a TRR file that I think this has solvent. I spell it right.
Yeah.
And if I do set on that, I'll get a set of all the different residue names. And I'm going to assume that sol is solvent. So I found one. So the thing I was saying before is you could just have you just wanted to ignore them, like I was saying, you can sort of say not, for instance. So that's how I get that. And it's funny that this number 3341 is similar to this number 3341. Yep. That's not a coincidence. So you could do that. And I'm saying that you could do your analysis and ignore the water. But if you wanted to create a new trajectory that was ignoring that, we didn't really cover writing trajectories, did we? Or
no, we didn't. So yeah, go ahead.
I'll show you how to do that. So if you did with MDA.writer, where you can look at the help for MDA.writer here. It wants a file name, it wants a number of atoms, and then there's some extra keyword arguments that some formats use. But basically, once a file name and a number of atoms is what you need to know. You could make a file name called dry.trr, and atoms is going to be the length of our not group. That's as W's. This is a bit of Python syntax where this function here gets assigned to this variable, but it's within a with block. Then you can say for time step in u.trajectory. And because we're trying to save some file space, let's say we're doing every 5th frame, just to play the game a bit more. You can then do w.write, not water. Cool. And so I've made a dry trajectory there. The other thing I probably have to do is then make a topology to go with it. So I can also do not water.write row. And what I can see is I've made a file called dry.grow, which has the magic number of 3341 atoms in it. And so then I could load a new universe from dry.grow and dry.trr. Sorry. And so we can see here we've made a new universe from files we just created from the old universe, which doesn't have solvents. So if you wanted to trim down your trajectory, this would be a way you can do it. And here I've trimmed both the trimmed out the solvent and I've trimmed out the trajectory. If you really wanted to save file size, you'd probably save as XTC, wouldn't you? So you can even change format this way. So if you ever want to convert a DCD to an XTC so that you can analyze it in GROMACS, you can do that in about 7 lines of MDAnalysis, and that's also a good use of MDAnalysis. It's just to convert between formats and never use it for anything else.
So the other and another note that we haven't actually explicitly covered, but I think maybe we should kind of say out loud is what happens if your topology and trajectory files have a different number of atoms?
Yeah, then you're gonna have a bad time.
That's not nice.
No. So let's entertain the question though. So basically, this TPR file is for my solvated system. If I put in the TPR here, it's gonna. Does it give me a good error message? Yeah, there you go. It says the topology and the XTC trajectory files don't have the same number of atoms. This has 47,000. This has 3,000. You're gonna have a bad time. The way that you would have to fix this. Sorry, I should keep this working so people can use it in the future. So this was the error message we got before. Bad times. You can make a universe which doesn't have a trajectory attached. So here I'm just loading the topology. So this is just the topology. I don't think there's positions. I can't remember if we load the positions from a TPR file, because there are positions in there. No, we don't.
No.
We should. So what I could do then is I could then do the same trick of, atom group. And I can see that I've made an atom group from that, and I can then write that to, let's go XYZ just to be, no trajectory. I can't create an XYZ file.
Yeah, because you don't have positions. We just checked that.
But is it going to complain about a grow file?
Yes.
It's going to complain about a grow file. That's frustrating. It won't just work. I'll do that.
Can you pass the positions as an optional argument, maybe?
Oh, that's what I can do. That should work though. I might fix that in MDAnalysis because that's frustrating, because my example that I thought was going to be very smart didn't work. Then what you can do is when you create your universe, if you pass in a NumPy,
You need a parenthesis. No, you need another parenthesis.
No longer,
Yes.
hasn't it?
99%.
99% parentheses. So what I've done here is that I've the trajectory file that I've passed in has been a NumPy array. So this has shape 1 frame, 3,341 atoms by 3 dimensions, X, Y, Z. And now my trajectory is right, sorry, it's the wrong number of atoms. It's been a long day.
Yeah.
Now my universe, I passed in a NumPy array of zeros, and it's loaded that with the memory reader. So basically, a weird trick of MDAnalysis is if you pass in a NumPy array, it will use that as a trajectory. So now I can select my dry atom group, write it out to dry.grow, and I can see that my dry.grow file has zeros as all the positions, but I don't care about that because I'm just using its topology, and so it has all this nice information on the left here of the residue names and atom names. So that was a fun question and led me to a something I might fix.
Yeah, we have another question. That's an interesting question. And I'm not sure that I would do it in the way that you're describing, but maybe you have something very precise in your mind that for which that is probably the fastest way. But so I'm gonna just repeat the question. I don't know, Richard, you probably didn't hear that. Yeah, so the question was, can you trick MDAnalysis, or can you create a system in which you can place dummy atoms in specific positions? So then, in order to apply some kind of artificial constraints to your MD, and yeah, you can definitely create a new system because you can combine the kind of create empty universe. You can apply, you can add positions as arrays. And if you have like a certain way of generating the positions in your box where you think those dummy atoms should go, you can definitely do that. But from there to use that as I guess the frozen atoms as a way to block your real atoms from going into that space, I don't know if I would do that, but I guess maybe you've got something in mind that I don't know, so maybe.
Yeah,
I guess you can create things and you can write them and you can read them and you can convert files and you can create bouncy dummy atoms with all fake attributes. We are not responsible for what you do with those files.
Yeah. So, I mean, this is cheating a bit because I've used RDKit, right? So I've already cheated in the first cell of this answer. So I'm a terrible person, but here I've used RDKit as a way of generating coordinates because it has a conformer generation code path. There's lots of ways you could do this. So I've made a propane molecule here and I've generated some coordinates for it. So if you're not familiar
You've
with
not added hydrogens.
chem.add H's, there you go.
Oh yes, sorry.
There you go. So we've got a propane conformation here. And thanks to one of our lovely Summer of Code students who is now working in industry, you can make a universe from an RDKit molecule here. So again, instead of passing a file into mda.universe, I've passed in an RDKit molecule. But it made a universe which has atoms, it has positions, and it has names. I think it has elements.
Quick question for the people in the room and on Zoom as well. How many of you use or have used RDKit?
Not
Okay.
many, I'm guessing. A few? I can't see. A few, okay. I think it's a secret weapon if you're doing MD. If you can sometimes know how to use RDKit, people think you're some sort of wizard because you can do things. Anyway, sorry, the question was, could you then use this for universe manipulation? So here I made a propane molecule. If I then wanted to solvate a box with propane molecules, you could put this in a loop and then merge them together. Or how would I do that? So for I in range 10, Actually, what I'm going to do is I'm going to say universe is equals universe of my RD mole for I in range 10.
Can you not pass a list of RD molecules to make the universe instead of making
I
a list
doubt
of
that.
universes?
I doubt that.
Okay.
And so then what you can also do is you can say for I, you enumerate universes, atoms.translate I times 10, 0, 0. I think that's how translate works. No, you need to give it a list. So, sorry, slower. I'm looping over my universes with an enumerate, which gives me a counter for how many universes I've looped over, which will be this I variable here. I can then translate them in the X direction by I times 10 nanometers. So the first universe stays in place, the next one will be 10 angstroms across, and the next one will be 10 angstroms across. And so I've gone from one molecule 10 times overlapping itself to 10 molecules which are separated by 10 angstroms. And I could then do MDA dot capital universes. Why has that not worked? I know what that is. It's atoms for universes. It wants atom groups and universes. Nope. It wants this. So it wants you to give it as many different atom groups as you want. So here I've done a terrible way of solvating or creating a propane box. I would not recommend this. I would use PacMol instead, but theoretically, yes. The best type of correct. Do we have any more questions?
Mm. No, I don't see any questions.
That's fine. I think the point maybe that we were trying to get across in this session is we showed you a lot of basics today, but it can actually be quite powerful if you wanted to do strange things. So even if MDAnalysis doesn't do what you want it to do, it's often a good starting point for the weird and wonderful places you want to take it. I think half the time I've been using MDAnalysis, I wasn't actually using it for what it was designed to do or what it was made to do. But it's always been a good starting point for sort of loading your data. So often I just used it to load files rather than actually using it for its intended purpose. But
We have a question in the chat.
Yeah, can we use NGLview? Yeah. NGLview works half of the time for me, if I'm being honest. So I have no idea if this is going to work. And this is because it's really hard to make Jupyter widgets. This isn't bashing NGLview, this is just Jupyter widgets are hard. But ooh, there you go though. So there you go. It did work. And if I is this gonna work?
Uh-oh.
Oh, yeah,
Yes.
here's my conga line of propanes. There you go. My pride and joy. Look at them all. I've made a crystal of propane. I'm so proud. So yes, you can use NGLview. So it has this show MDAnalysis method, which will render an MDAnalysis universe.
You've not actually answered the question, but so the question was, can we visualize properties along the trajectories?
Sorry, my bad. I should learn to read questions.
The short answer is no, because NGLview is not very flexible.
Sorry, I'll get rid of my crystal here. Oh wow! So we've learned something about wrapping proteins today already, but we can see this isn't quite wrapped properly. You can press play on it and you can see it do its little dance. This is the dance of its people. You can't maybe see the hydrogen bonds and you can't see any properties, but you can definitely inspect what's going on, and we can definitely see that we haven't properly imaged this this molecule.
I mean, personally, my use of NGLview is just if I want to eyeball my atom selections and I just want to sanity check myself. That is the main use. So it's not something like powerful like VMD that's going to, you know, enable you to measure things and do a lot of complicated stuff, because of like the widgety environment is not quite as good as something that you would have in PyMol, in a Chimera, in VMD. So if you want to do anything that's like heavily visual and a mix of kind of analysis and qualitative, go there. But NGLview is good as a sanity check. Yes. But the other thing that I was thinking is, yeah, we haven't actually demonstrated the make whole and the wrapping. So if you want to, yeah, go ahead and do that.
Yeah, and
That's
this
a very
is a
good
bit,
trick.
this is a bit hidden away. I need to maybe publicize it and document it more. There is a function called make whole. This will, how to explain this? It won't put everything in the primary unit cell. It will make each molecule never have a jump along a bond. So you know how sometimes a molecule will be split in half, and so the bond will be much longer than it should be. This will make bonds always the right length. So every atom is in the same, no, is in the correct image compared to its neighboring atom, but they might be in different images. It gets a bit confusing. And it won't mean that all fragments are in the same image as each other. That's the make whole.
Yeah, just like in the box that you had just
yeah, sorry. Let me just show you what I mean. Thank you. It's almost like you're a professional teacher. So we can see here that sort of the top half of this loop, this top half of this protein is obviously should be over here connected to the top half of the protein here, but instead it's gone whoop, over here. And NGLview is trying its best to display that nicely, but ain't good. So what you can do is you can say for atom group in u dot atoms dot fragments. So fragments is all of the discrete molecules. You can only say make whole. How you spell the word whole? That. And then you can do. Why has it done that though? Computer says no.
You have to do it for the whole trajectory. You have to iterate over the trajectory.
I think it's that when you do it in NGLview, it loads the file again, so it goes back to the old coordinates. But I think if I do it in memory, then it changes the coordinates in place. So now, oh, but it doesn't do the first. So so we did the first frame, but we didn't do the second frame.
Yeah,
so,
as I said, I think you need to do it in iteratively. Yeah.
I think it's also that when you view it in NGLview, it loads the file again, so it will get rid of all the old modifications you made to your positions.
But then in that case, you should be able to see it if you use the same Jupyter notebook cell. No, see, now it works.
Now it works, but I think it's working because I put it in memory. It's a quirk.
Interesting.
I do, yes. I do. If I do atom group dot bonds dot values thing. Yeah, PBC equals false. This will calculate me the length of. Why is that not working? It's got 0 bonds. Why does it have 0 bonds?
Because you haven't guessed bonds.
No, it's because it's the last atom group in the universe. It's an ion. So it doesn't have any bonds. Sorry. If I look at all the bond lengths with PVC off, so it won't do any imaging. And if I look at the max value of that, it's 1.8 angstroms, which isn't too big. And if I comment out this line about making whole, I get 80 angstroms. So yeah, that's the difference in making whole, is all your bonds will be the right length, or will be an appropriate length for visualizing. I'm not sure if I answered any questions there, but probably raised a few.
So
that's fine. The other thing that I should maybe highlight or promote is that if you have future questions along anything to do with MDAnalysis, there's 2 places you can ask those. There is a GitHub discussions board. So if you go to GitHub, if you find the MDAnalysis project on GitHub, which I think Jenna is actively searching to post to the chat, there's a discussions forum where you can ask any question, and then someone like me might answer it if they think it's a fun question. We generally try to answer questions there. So that's one place. And then the other place is we have a Discord server where similarly you can ask questions about, how do I do this with this? Has anyone ever done this before? And there is a bunch of people that have been playing with MDAnalysis for a while that might know how to answer your questions there about, like, how do I do these crazy things? Because there's a lot of people that have tried and failed at various things with it before. Like, it's been going for over a decade now, so there's a lot of people that know how to do a lot of things. And with that, I'm going to hand back to you, Dr. Matta.
now the first thing I want to do, I just want to invite everyone to give us your feedback about this session. So please, you have a survey here. We're going to ask you about a couple of questions about how you found this workshop. And there's also the Discord invites and a lot of other links, useful links. And yeah, so I'm going to just leave that for a couple of minutes. So we are trying to be better at recording these kind of events and posting them on YouTube. So this is, this is being recorded. You can go back and kind of check the materials again. You can go and, listen to us rambling again on YouTube if you so wish. And if you have any follow-up questions, please let us know on Discord or on GitHub discussions. And we are constantly running new workshops, and each of them has a slightly different flavor. So for instance, a few months ago, we had a workshop that explored how to integrate the which is a visualization software for creating cool 3D images, and MDAnalysis. So you want to go out and check. So if you are interested in rendering 3D visualization stuff, that's one for you to check out, because I think Blender is an amazing software and it allows you to do a lot of cool stuff that is beyond what VMD or PyMol can let you do. And so if you have some cool images from your project that you want to turn into like the next killer cover of your next first author paper, that is the workshop that you wanna check out that recording when it comes out. The other thing is we are organizing our second UGM user group meeting. So all of you are surely you are more than welcome to check out. This is going to be, I was already talking about it during the coffee break, but yeah, it's going to be at the end of August at King's College London. We are partnering again with the TYC for this. And we're going to have a couple of invited speakers. We're going to have industry, people from industry, people from academia using MDAnalysis in many different ways. And we're going to have a lot of interesting talks from early career researchers, professors, postdocs, all across the board. We're gonna have open discussions between core developers and users, and we're gonna have a hackathon on the last day, and a welcome a poster session with drinks and other social stuff that we will organize. So our keynote speakers, one is Dr. Antonia May, who works at the University of Edinburgh. She works at the interface of molecular dynamics and machine learning. And the other one is Francesca Stanzione, who works at Societae Heptares over in Cambridge. Yeah, so they're gonna show us how they use MDAnalysis in their work. Great, so stay tuned to register for this event. And yeah, so I guess that brings us to Richard, do you have the MDA kit stuff ready to go?
Yeah, we have a scheme where people can contribute their analysis code into what we call an MDA kit. So if you've made something which is possibly useful to other researchers, or perhaps you're looking at publishing some work and you want to also publish the software alongside that, we have a pathway for people of packaging of their work in a way that's then useful by other people. That's called MDA kits. If you go to the website, I think there is some links to that there, and Jenna has also posted a link in the chat. So we have this pathway for publishing your work there. Something I've found is that if you publish your software in a way that other people can use and download it, you get a bunch of citations for things you never thought were relevant to your work, but just because you packaged up your code in a way that people could use. So if you want to play the game, that's how you can play the game.
All right. Jenna, do you have any final notes?
Yeah, I was just going to say, we've just, especially in the last few minutes, thrown a lot of resources at all of you. And I know that people in the room might not necessarily be following along on Zoom and seeing everything that's going up in the chat. Just wanted to say, don't panic. Don't worry about throwing this all down if you missed anything. This is all going to be in follow-up communications that you get from us, and details with the recording. So you'll be able to access all of this after the workshop, not to worry. And we can even put things on the repo as well, anything that was referenced. So we've been tracking things that we talked about today to make sure you have them afterwards as well.
Yeah, sounds great. So I guess we're gonna start wrapping up, and you know, we'll be here for a little longer if you have any lingering questions, but yeah, I think that's all from us, unless there are any last minute questions from either the room or in the chat. Yes. Did you hear that, Richard? Is there a specific are there some analysis, for instance, for the electrostatic potential or things like that? I think I'm not actually sure. I don't think so. I think when I calculated the I had to do that once, and I don't remember it. I don't think I used MDAnalysis, but I now I also cannot remember what I used. So maybe GROMACS, potentially GROMACS. Yeah. No, we don't necessarily cover a lot of the kind of other, you know, this kind of there's some built-in functions, right? Some of the kind of, mostly for biomolecular simulation, the most common use cases, but a lot of the development is just down to what the people at the time were working on, right? And so sometimes, you know, like some of the code, so for instance, I think the persistence length and some of the polymer stuff, Richard wrote it when he was working on a polymer project, right, in his PhD. So yeah, I guess it's down to like if you have an idea, or if you have some code that you think, you know, or something that you think we should, you know, implement, yeah, let us know in the discussions, open an issue, I don't know, talk to us. Yeah. All right, so I'm gonna say thank you all for joining, both online and in person. And yeah, hopefully we'll hear from you. Looking forward to seeing your feedback as well. Thank you so much. Jenna, Richard, thank you so much for everything. And yeah, take care.
Yep, thank you all. Thanks for
Thank
joining.
you.